quick review of the property: ionization energy increases as we go across. Remember that the nucleus is stronger, it's holding on to the electrons with more power, with more strength, and so it takes more energy to remove an electron as you're going across. As you go down, it is decreasing, and that is because we're adding those additional energy levels. The electrons are being placed farther and farther away from the nucleus, and it's easier to take an electron farther away from the nucleus than it is one that is closer. We were just talking about removing a single electron from an atom. But what if you wanted to remove a second or even a third electron from an atom? This is called successive ionization energies. As long as you have the energy required to remove that electron, you can forcibly take electrons away from atoms. What you need to know is that removing more and more electrons requires more and more energy, so the cost is going to get pretty high. The remaining electrons are more tightly bound to the nucleus every time you take an electron away, and so that means that there's a tighter hold to the nucleus, and that's just going to require an extra amount of energy. Let's take a look at the successive ionization energy chart at the bottom and focus in on sodium. You can see as we go from the first removal to the second removal to the third removal to the fourth removal that more and more energy is required, like we said. But where do we see a drastic change in energy? And that's happening right at this mark right here. The difference between the energy taking one electron away versus two. Well, if we go back and we look at the electron configuration for sodium, which is 1s2, 2s2, 2p6, 3s1, we know that if we remove an electron from the outermost energy level, that will wipe away the third energy level, leaving me with the highest energy level of 2, and a total of 8 valence electrons. It's going to take a tremendous amount of energy to break that octet up, to remove one of those electrons that is being so tightly held to the nucleus in the lower energy level of 2. If you look at anywhere on the chart, you will see that there's always going to be a place, let's take a look at silicon, where you're going to see that gradual change in ionization energy, but then there's going to be that huge jump. And that's just a way to indicate to you that you're actually removing all the electrons within the outermost energy level and moving more into the inner core electrons to a lower energy level. We take a look at silicon. Silicon is 1s2, 2s2, 2p6, 3s2, 3p2. So to remove one electron, not that big of a deal. To remove 2 electrons, we completely get rid of the 3p sublevel. A third electron would remove one from the s, but to remove a fourth electron would put us then now at that lower energy level again. So that fifth electron doesn't want to be removed, and it's going to cost a lot of money if we're going to, or a lot of energy if we're going to remove it. All right, let's discuss our third property, electronegativity. Electronegativity is the tendency of an atom to steal or take an electron from a different atom when combining with another element. Fluorine happens to have the highest value, and francium has the lowest value, and this will help you make the prediction for period and group trends. As mentioned, we said that fluorine has the highest electronegativity value, and francium, cesium, has the lowest. So it should make sense that as we go across, you're going to see an increase in electronegativity and a decrease in electronegativity as we go down, just based on knowing those 2 points of interest. Now, why does this happen? Once again, we got to go back to the strength of the nucleus and think about what electronegativity means. It's the desire for an atom to steal or take an electron from a different atom. So it all comes back down to that nucleus. Is it strong or is it weak? Once again, we know as we go across a period that we're going from 3 protons versus 4. We know that the beryllium has the stronger nucleus. Stronger nucleus is going to pull electrons in closer. So not only does it pull in its own electrons closer to the nucleus, but it can actually pull electrons from other atoms as well. So when an atom is smaller, the nucleus pulls more strongly, and this can attract and draw an electron away from another atom. As we go down in group, electronegativity is decreasing. Remember that the additional energy levels play a role in that. Since every time we add an additional energy level to the atom, the nucleus has a harder time dealing with those outermost electrons due to the shielding of the inner core electrons. That's also going to help us explain why the nucleus is not going to be able to grab an electron from a different atom. It's not going to be strong enough to pull an electron from a different atom due to the fact of this shielding. So the larger the atom, the less able the nucleus is to attract electrons away from a different atom. All right, let's take a look at this example. Who has the highest electronegativity? And we have been given barium, bromine, and calcium. Here's another example of a pattern that is not a pure group or pure period trend. So we do once again have to look at I of Zorro. Remember that it is the third line of the Zorro signature that represents electronegativity. And we talked about whatever movement of the sword, in this case it's going up again, is an increase in the property. So as we go from lower left to upper right, that is going to be an increase in electronegativity. And so that means for us that bromine is going to have the highest electronegativity value. Notice that that trend is very similar to the trend of ionization energy. They move in the same direction. The last example would be looking at I, Br, NCl. That is a pure group trend, and we know as we go down, ionization energy is decreasing. We're getting farther away from fluorine. So if we had to put these in decreasing order, chlorine would be the greatest, then bromine, then iodine. Quick review of electronegativity. As we go across, the trend is going to increase. One of the ways to remember that is fluorine has the highest electronegativity value of 4.0 Paulings, and cesium has one of the smallest. So that would explain the decrease. And remember that it really has to do with the strength of the nucleus. As we're going across, the nucleus is getting stronger. Not only can it pull on its own electrons with more intensity, but it can also pull on electrons from different atoms and take them over. And with the decrease, which is the group trend, we know the additional energy levels are causing the nucleus to get weaker, so it doesn't have as much strength and it can't pull electrons away from other atoms.